Welcome friends to the another session on the transistor amplifier. In this session, we will be discussing about the transistor bias variations. You will find that the biasing of the transistor is being affected by many parameters, and therefore in an electronic circuit, there is always change in the bias values of the transistor. In this session, we will see what is the need of the biasing, what are the factors that affect the bias variations. We will describe the concept of thermal runaway of the transistor. We will also define the stability factor of a transistor, and then we will determine the stability factor for common base and common emitter configurations of transistor. As you know that you are viewing this session on my YouTube channel, Learn with Prakash Khanale, and don't forget to subscribe to the channel. So let us start our session with what is the need of the biasing. We know that a transistor is a three-terminal device where the first terminal is emitter, second terminal is base, and third terminal is the collector. Whenever we want to use this device in any electronic circuit, then we must provide appropriate DC voltages to the emitter terminal, to the base terminal, and to the collector terminal of the transistor. Without providing these DC voltages, you will find that the transistor will not work. Also find that when we provide these DC voltages, then that is being called as a biasing of the transistor. Now, when we want to use the transistor as an amplifier, then you will find that we need to keep it in the active region. That is, its base emitter junction must be forward biased and its base collector junction must be reverse biased. So this can be achieved only with the proper biasing of the transistor. That is, we can keep our transistor in the active region only when we provide appropriate biasing to the transistor. You will find that if the transistor is not biased properly, then the output of the transistor may not be a perfectly sinusoidal when a sinusoidal input is applied. In that case, you will find that the output of the transistor may be a distorted output. Also, you will find that with the help of the biasing circuit, it is possible for us to stabilize the Q point or the operating point of the transistor at the center of the DC load line. If the biasing circuits are not used, then you will find that the Q point cannot be stabilized. So these can be the various reasons why should we go for the biasing of the transistor. With biasing, we can fix the position of the Q point. With biasing, we can get a better output or undistorted output. With biasing, we can keep the transistor in active region. And with biasing, you will find that the transistor in any electronic circuit will work properly. But you will find that it is very difficult to keep the bias of the transistor fixed. There are various factors that affect the bias or that causes variations in the bias values of the transistor. You will find that the Q point or the operating point of the transistor does not remain stable, and it has a tendency to shift its position. When the Q point of the transistor shifts its position, then this is being called as a bias instability. And this bias instability is because of the thermal instability of the transistor. You will find that any electronic circuit, when it is kept on for a long period of time, the temperature of the electronic circuit increases. Similarly, when the transistor is being operated over a long period of time, the temperature of the transistor increases. And due to the variation in the temperature, you will find that the collector current of the transistor will increase. And when the collector current in the transistor will increase, it will ultimately shift the position of the Q point of the transistor. For any common emitter circuit, you will find that the collector current of the transistor can be given by this equation. The collector current IC is equal to beta times IB plus ICEO. The same expression can also be written as beta times IB plus this ICEO can be replaced by 1 plus beta times ICO, where this ICO is a leakage collector current and beta is the current gain of the transistor, and IB will stand for the base current of the transistor. So you will find that in this equation, IB, beta, and this ICO, all these factors will depend upon the temperature. And when the temperature is increased, then it will ultimately causes change in these values. And therefore, the collector current will increase. And this phenomenon is being known as the thermal runaway of the transistor. Now, as shown in this diagram, you will find that when the power dissipation of the transistor increases, then it will cause the increase in the temperature of collector base junction. It will ultimately cause an effect on the resistance of the device, and the resistance will decrease. When the resistance decreases, it again increases the collector current IC. When IC increases, then again the power dissipation increases. So this cycle continuously goes on, and because of this, you will find that the transistor will get heated, and when the transistor gets heated, then there ultimately its effect will be on the variation in the bias values or on the position of the Q point of the transistor. You will find that it is practically possible to design a biasing circuit in such a way that when the temperature of the transistor increases, then ultimately we can make the circuit arrangement such that IC will not increase. That is, IC will get decreased with the increase in the temperature. When IC will get decrease in the increase in the temperature, then you will find that the further rise of the IC will be compensated. And if such arrangements are made in the biasing circuits, then you will find that the bias stability of the transistor will increase. So in the next session, we'll be discussing about the various biasing circuits of the transistor. And in these biasing circuit, we will see that how the IC is being kept constant, even if beta is changed, or even if the temperature of the transistor is changed. Now we are in a position to define the stability factor for a transistor. Stability factor, you can say, it is a kind of a measure of keeping the collector current constant in spite of the variation in the leakage current of the transistor. Because we know that when there is change in the leakage current, then ultimately it causes change in IC. And when IC gets changed, then it causes the variation in the stability of the transistor, or the biasing of the transistor gets changed. The stability factor is being defined as the rate of change of collector current with respect to the leakage current ICO. And the condition is that the beta of the transistor, that is the current gain of the transistor, and the base current IB are constant. We can write a small formula for the stability factor like this. The stability factor is normally indicated by a symbol S. S is equal to DIC divided by DICO, where DIC will stand for the change in the collector current, and DICO will stand for the change in the leakage current of the transistor. You will find that for any transistor, this stability factor should be as low as possible, because you will find that even a small amount of change in ICO will causes a larger amount of change in the collector current IC. And therefore, we want this stability factor to be very low. And you will find that the most ideal case for this stability factor is the value 1. Now we can determine the formula for the stability factor. Suppose the collector current of the transistor is being given as beta IB plus ICEO. The same can be written as beta times IB plus 1 plus beta times ICO. Now, if I differentiate this equation with respect to IC, since I am differentiating with respect to IC, here I will get on the left hand side 1, which is equal to beta times DIB upon DIC plus 1 plus beta times DICO upon DIC. Now you will find that the same equation can be written as, we know that the stability factor S is equal to DIC upon DICO, and therefore this term can be replaced by 1 upon S, and therefore we will get the equation 1 is equal to beta times DIB upon DIC plus 1 plus beta times 1 upon S. Now we can easily write the formula for S. Stability factor S is equal to 1 upon beta divided by 1 minus beta into DIB upon DIC. So from this expression, what we find that the stability factor of a transistor will depend upon the beta value of the transistor. It will also depend upon the base current IB and the collector current IC. Now let us determine the stability factors for common base circuit and for common emitter circuit. We know that the transistor can be used in common base configuration, where the base terminal is made common to both input and output. And in case of common emitter circuit, the emitter terminal of the transistor is being made common to both input and output. For common base circuit, you will find that the collector current can be written as IC is equal to alpha times IE plus ICO, where alpha is a parameter of which the value is very close to 1. Now, if I differentiate this equation with respect to ICO, then I will find that DIC upon DICO is equal to 0 plus 1. Since I is constant, and therefore its differentiation will give me a 0 value. And when ICO is differentiated with respect to ICO itself, then it will give me 1 value. And therefore, you will find that for common base circuit, the value of S is equal to 1. So as far as the stability is concerned, as far as the stability factor or biasing stability is concerned, you will find that the common base circuits are the ideal choice. Now, the same factor, stability factor, can also be determined for common emitter circuit. In case of common emitter circuit, we know that the collector current IC is equal to beta times IB plus 1 plus beta times ICO. Now again, if I differentiate this equation with respect to ICO, then you will find that DIC upon DICO is equal to 1 plus beta times, because this first term will give me 0 and this second term will give me the value 1 plus beta times. And therefore, the stability factor for common emitter circuit S is equal to 1 plus beta times 1 plus beta. So here you will observe that the stability factor for common emitter circuit is much higher than that of the common base circuit, because the value of the beta can be a 2-digit number or 3-digit number. Say for example, if the value of beta is 20, then the stability factor will be 1 plus 20, that is 21. So for common emitter circuit, you will find that the stability factor is bit higher than that of the common base circuit. So as far as the biasing stability is concerned, you will find that the common base circuits are superior than that of common emitter circuits. So hopefully friends, you have understood some basic terminologies that is being used in transistor biasing. If you have any questions in relation with this, then you can write to me or you can ask these questions in our oral discussion. Thank you for viewing this session. Thank you all.